improve safety and to increase productivity are two of the major imperatives facing the South African gold mining industry today. Large tunnels are the vital arteries at the heart of a mine, and these have to be kept open for the life of the mine, often in a hostile and changing environment. In the present climate of high-cost capital, the viability of new ultra-deep mines may depend on whether these new arteries can be created more speedily and more safely than has been possible in the past. The demand for greater safety dictates that support must be applied right up to the advancing tunnel face. The demand for greater speed requires that the support cycle must be closely integrated into the total development cycle of drill, blast and load out of the broken rock. Existing tried and trusted methods based on rock bolting with mesh and rope lacing cannot meet these requirements. These methods are slow, labor-intensive and therefore costly. Because more people are involved, the safety risk is also increased. It seemed that innovative approaches had to be adopted and new technologies explored in order to overcome these problems. Recognizing this some 3 years ago, Johannesburg-based engineering consultants Stefan, Robertson and Kirsten embarked on an initiative aimed at exploring the potential of shotcrete as a means of solving the particular problem of supporting deep high-speed tunnels. It was appreciated that shotcreting is not a new technique. It had been tried before on deep mines with mixed results, often disappointing, sometimes encouraging. There was general agreement, however, on three things. Wet mix shotcreting required cumbersome equipment, a costly infrastructure, and was operationally inflexible. It could, however, produce a high-quality product in large straight tunnels and in large chambers. Dry mix shotcrete, on the other hand, was more suitable for use in smaller remote tunnels, but suffered from slow rate of application, inconsistent quality, and created nearly intolerable environmental conditions because of excessive production of dust. Finally, unreinforced shotcrete of either type tended to be brittle, with the result that very small deformations could cause cracking and detachment from the rock surface. SRK were aware that there had been significant advances in shotcreting technology in civil and structural engineering, and in particular in the form of dispersed reinforcement. This type of reinforcement consists of fibers of steel or polymer, which are included in the shotcrete material prior to its ejection at the nozzle. The initiative adopted by SRK was the creation of a shotcrete working group, that is, a collaborative association of a broad range of interested parties such as machine manufacturers, material suppliers, designers and consultants, customers and consumers, who in their own diverse ways would benefit from the attainment of a solution based on fiber reinforcement shotcretes. A modest investment from each member organization would enable the group to fund jointly research or development that any individual company on its own could not justify. At the outset, the working group decided that there had been a paradigm shift in design philosophy between that required from the civil engineer and that appropriate for the large deformations that were inevitable in deep tunnels. Where there is no external stress change and appearance, and water tightness are important, the lining must be strong, inflexible and smooth in finish. Deep underground, where fracturing of the surrounding rock is unavoidable and deformations are large, strength is relatively unimportant, but compliance or ductility is vital. It was decided by the working group that the essential criterion of adequacy for highly stressed tunnels was that the shotcrete should sustain a deflection of 150 millimeters across a span of 1 meter between adjacent supports, while retaining a residual strength of at least 1/2 of the peak strength. Thus, yieldability or compliance was the important requirement rather than high compressive strength. During the past 2 years, the working group has conducted nearly 60 load deflection tests on large shotcrete slabs reinforced with various types, lengths and contents of fiber. From this laboratory research, the working group showed that the criterion of performance of 150 mm deflection could be met without undue loss in strength. The strongest fiber reinforced shotcrete was found to be that based on 40 mm long Dramix steel fiber. A 40 mm long polypropylene fiber produced a shotcrete which also retained more than half of its peak strength. It now remained necessary to show that dry mix fiber reinforced shotcrete of the necessary quality and uniformity could be produced under normal operational conditions in remote parts of the mine. Most importantly, during the course of the research which led to these findings, MASH Engineering, one of the founding members of the working group, has made major improvements in the application technology. Their shotcreting machine was very compact, weighed only 700 kilograms, and applied shotcrete at a high rate with very little rebound loss and virtually no dust. The improvements in rate of application, reduction in rebound losses and levels of dust created were so dramatic that it was felt that producing a video intended simply to demonstrate these achievements was fully justified. The shotcrete material is supplied in sealed bags by Rockstay. The material has been pre-mixed for 4 minutes to ensure homogeneity of the fly ash, silicate fume and fibers in the aggregate. During operation, the contents of the bags are simply fed into one hopper on the mixer unit. The material has a moisture content of 10%. General dust suppressant, GDS, as a powder additive in the mix, effectively reduces dust at the machine and, more importantly, prevents segregation of the fibers during the passage of the mix through the machine and through the material hose to the nozzle. Cement is fed into a separate hopper on the mixer unit where the ratio of material to cement can be precisely adjusted to desired strength requirements. Mixing of the cement and the Rockstay takes place in the feed screw conveyor. The feed screw discharges into the rotary drum of the shotcrete machine at 6 cubic meters per hour, which is sufficient to apply a 50 mm thick cladding to an area of 70 square meters. The dosing water added to the nozzle has the GDS additive in it in liquid form, which ensures that all the particles are wet when leaving the nozzle. GDS liquid has several important benefits. It dramatically reduces dust and misting. It reduces rebound loss of fiber and aggregate to approximately 5%. Under wet ground conditions, it helps prevent wash away from occurring while the cement is still hardening. It reduces migration of water to the substrate being sprayed. Finally, it forms a waterproof membrane on the surface of the shotcrete, which is essential for optimum curing. The Rockstay shotcrete system balances the material, logistics and technical requirements necessary to provide the best quality shotcrete in a much more cost-effective manner than was ever possible before. The working group is confident that it has demonstrated that shotcrete, with suitably chosen dispersed fiber reinforcement, can maintain adequate strength while sustaining the large deformations inevitable in deep tunnels subjected to high stresses and large stress changes. Moreover, it has demonstrated that this type of shotcrete can be applied by the dry mix method at a sufficiently high rate with negligible production of dust and minimal rebound loss. There is real hope that it will go a long way towards increasing safety and productivity in high-speed deep mine tunnels. The health and longevity of the vital arteries will thus be ensured and the profitable life of the gold mining industry prolonged well into the new millennium.